Our learning target is here. We're going to learn how to interpret orbital diagrams. So we're going to draw them and know several things about them. So you can read through the learning target there. So before we can really start talking about orbital diagrams, we need to talk about the 4 quantum numbers. The 4 quantum numbers basically are a set of directions that tell us where the electrons are in an atom. And there are 4 of them. They're represented by N, L, M, and S. So you're going to need to be familiar what each one of these stands for. So N is also called the principal quantum number, and we've seen N when we've talked about energy level in the Bohr diagrams. So this is going to tell us the average distance from the nucleus and the cloud side. So basically it tells you about how big your atom is. Now you need to be familiar with this formula. The maximum number of electrons in an energy level is 2n squared. So whatever the energy level is, you square that and then multiply the whole thing by 2 to give you how many electrons can fit in a given energy level. So in the first energy level, where n equals 1, 1 squared is 1 times 2 is 2. So the first energy level is going to hold 2 electrons. The second energy level, 2 squared is 4 times 2, so the second energy level can hold 8 electrons, and so on. So whatever your energy level is, square it, multiply it by 2, that'll tell you the maximum number that it can hold. Now L is the sublevel. Now the number of sublevels in an energy level is going to be equal to whatever N is. So for example, if N, the first energy level, N is equal to 1, so there's only 1 sublevel. N equals 2, so the second energy level has 2 sublevels. The sublevels are described by the letters S, P, D, and F, and we are going to use a lot of S, P, D, and F. So you need to memorize these along with the maximum number of electrons that each one can hold. So S can hold, whoops, there we go. S can hold 2 electrons, P can hold 6, D can hold 10, and F is 14. So memorize this right here. S is 2, P is 6, D is 10, and F is 14. M stands for orbital. This is going to describe the electron's orientation or the probability of the location of an electron. And these are graphs based on probabilities. Now, something to keep in mind is that only 2 electrons can occupy an orbital. You're going to hear the term degenerate orbitals. They're going to have a different shape, but they have equal amounts of energy, and this happens in the P, Ds, and Fs. Each sublevel is going to have a specific number of orbitals, so you need to know these as well. So if S can hold 2 electrons, and each orbital can only have 2 electrons, then S can only hold 1 orbital. S only has 1 orbital. So if P has can hold 6 electrons, then it needs 3 orbitals to hold those electrons. D can hold 10 electrons, so it would have 5 orbitals, and F can hold 14 electrons, so it can have 7 orbitals. So again, 2, 6, 10, 14, make sure you know the maximum number of electrons, and then know that how many orbitals are in each sublevel. A lot of stuff to learn. Now here's example of S and P orbitals. So there's only one S orbital, so it's a spherical shape. P orbitals, depending on the axis that you're looking at, they have 3 different shapes. So your 2 px electrons could be anywhere in this area here. Your py electrons could be anywhere in this area, and pz could be here. Now if you put these 3 graphs together and add them all up, you end up with a spherical shape. So overall, a sublevel is going to look like a sphere when you add up all of its individual shapes. S is the spin. This is going to tell us the direction that the electron is spinning, either clockwise or counterclockwise. So electrons can occupy energy levels, then they go into sublevels. Each sublevel is divided into orbitals, and then finally in those orbitals they're going to be spinning in opposite directions. So here we have numerical values of plus 1/2 and minus 1/2 that correspond to clockwise and counterclockwise. Now we don't have to get into the numerical values of all these. You can take AP and have a ball with that. Alright, you need to be familiar with these three rules and principles. The Aufbau principle tells us that the energy levels are filled from lowest energy to highest energy. So the electrons are going to want to go in where it's easiest. So the lowest energy gets occupied first. Hund's rule says that each orbital has to be occupied before you can pair those electrons. So we'll look at that. And then the Pauli exclusion principle tells us that no two electrons can occupy the exact same location. They can be in the same energy level, in the same sublevel, in the same orbital, but then they have to be spinning in opposite directions. So we'll also look at that. Now here's an example of an orbital diagram. Now each of these little blanks represents an orbital. Okay, so this first one is in the 1s sublevel. There's one orbital. It can hold 2 electrons. Now we use half arrows to represent electrons here. And notice that one's going up and one's going down. That represents opposite spin. Then we have our second energy level where we can have 2 orbitals. We have an S, or we have 2 sublevels, so we have an S and a P. So that 2s is 1 orbital and the 2p is 3 orbitals. Okay? And these numbers here represent the order that the electrons are going to enter those orbitals. So the first 2 electrons are going to go in the lowest energy. That's the Aufbau principle. So the first 2 electrons are going to go into the 1s sublevel. They're going to go in opposite spins. Then the next lowest energy would be our 2s. So there's 3 and 4. Now we're going to go to the 2p. Now notice here we go 5, then we jump to the second p orbital. So think of these as px, py, and pz. These are degenerate. They have the same amount of energy, but what happens is you can only pair the electrons after you occupy each orbital. Remember that electrons are negatively charged. They're going to want to be as far away from each other as possible. So they're going to enter different orbitals to make that happen. So this is Hund's rule that we were talking about earlier. So each orbital has to be occupied before we go back and we start pairing. Now the Pauli exclusion principle tells us that 1 up and 1 down in each orbital. So we've covered those 3 principles. Alright, so orbital diagrams are going to look different depending on what you get them out of. A lot of times you'll see boxes, which is what I'm going to use here. So we're looking at phosphorus. So we need to know how many electrons are in an atom of phosphorus. So we're going to look on our periodic table, because remember that the number of electrons is the same as the atomic number. We're talking about neutral atoms here. So phosphorus is going to have 15 electrons. So the first 2 go into 1s. It's the lowest energy. They're going to go 1 up, 1 down. The next 2 are going to go in the 2s. Okay, again, 1 up, 1 down. Notice our energy is increasing here. So our next electron is going to go in the 2p. Now, we've got to go to this next orbital, and then finally the third orbital to satisfy Hund's rule. And then we can start pairing again. So at this point we have accounted for 10 electrons. Our next 2 are going to go in the 3s. Alright, now we're back in a p here. So we go 1, 2, and 3. Now we have 15 electrons, so this is the orbital diagram for phosphorus. And I did make a mistake here. There should be 5 orbitals on this 3D. So here is the orbital diagram for phosphorus. Now let's look at the orbital diagram for calcium. So first things first, we need to know how many electrons we have in an atom of calcium. So we look at our periodic table and we see that calcium has an atomic number of 20. So it has 20 electrons. So the first 2 go in 1s, then we go to 2s, and then remember in 2p we occupy each orbital before we pair. Now we're going to 3s. Now we're going to 3p, so again we're going to pair those, or I'm sorry, we're going to put one in each orbital before we pair. Alright, so that's 18 electrons. Now the next 2 electrons are going to go in our 4s sublevel before they go in 3d. Now here's why. 4s has less energy than 3d. There's some overlap that starts to happen in these outer energy levels. So remember, Aufbau tells us that we have to fill in order of lowest energy to highest energy. So because 4s has less energy than 3d, we are going to occupy it first. And there you go. There's the orbital diagram for calcium. Alright, what can you tell, which one of these orbital diagrams is incorrect and why? I'm sorry, which one is correct? I'm sorry. Which one is correct? Alright, A is incorrect because over here in 2p we did not occupy this third orbital. C is incorrect because we did not fill 2s before we jumped over to 2p. And D is incorrect for the same reason. We didn't occupy 2s before we went to 2p. So the one that is correct is B. And one more example. Which one of these orbital diagrams is correct and why? Well, A is incorrect because we did not occupy this last orbital. That's Hund's rule. B is correct. That's the correct one. C is incorrect because we did not fill 2s before we went to 2p. Now, if any of these arrows had been in the same direction, that would have been a violation of Pauli exclusion principle. So A is a violation of Hund's rule, where we didn't occupy each orbital before we paired. C is a violation of Aufbau because we didn't fill our lowest energy levels before we moved on.